Hi, everyone. Thank you all for coming. Great to see so many people here. My name is Oscar. I am from the developer relations team, and today we're going to speak about camera. In this session, we'll cover three major topics. First, we're going to talk about the inner workings of camera on Android. Second, Snap is here with us today. They're going to showcase how they use the camera APIs in production to millions of users. And we're going to close with our vision of the future of how camera API should evolve and the ecosystem that goes with it. Let's jump right in. Developing camera app is a series of compromises. Some are outside of your control as a developer, but understanding those will help you make better decisions where you have control within your app. Let's cover how camera works at the physical level. As any decent photographer knows, it is a pipeline of steps at the physical level. Visible light goes through a lens that directs it to filters, which passes the light on to millions of light sensors. Then that converts the light finally into a 2D matrix of pixels. When you think light sensors, the first name that may come to mind is the almighty CCD. Nowadays, we have many other kinds, such as CMOS or APS, that are actually more commonly used in today's modern cameras, DSLRs, phones, etc. From now on, we refer to this component as the camera module. The output of the camera module is a raw picture, a raw frame. It is not entirely unprocessed, but it has not been processed outside of the camera module at this stage. You can think of the camera module as a black box that dispatches these frames. In early hardware, we had 3 physical pins for different kinds of pictures. Nowadays, in modern designs, we have a single pin, thanks to tricks like multiplexing and higher clock speeds and so forth. But the conceptual model remains as having separate processing pipelines for each kind of image. We have, generally speaking, 3 broad use cases: video preview, photo, and video recording. We'll cover those separately. The camera module, as I said, is a black box, and it contains an increasing amount of smarts within, some of which are in a closed feedback loop. You, as a developer, we as developers will have very little visibility into what goes on in there. To give you an example, when you set, say, autofocus or auto white balance, the camera module may be looking for faces to see how to better optimize those settings, and you don't really have any control over that. From a framework standpoint, all developers do is send one configuration in, and you get one frame out. This is very, very important. You send one configuration in, one frame out. For each frame, there is a configuration that goes with it. To help you with this, we have a set of template configurations. We'll cover those later as well. So let's zoom into the preview pipeline, the one on top. As I said, each pipeline shown is a broad use case. When it comes to preview, you can think of it as the viewfinder. So whenever somebody is holding their phone up and you want to see what the camera sees, this is the use case we're talking about. We need to compromise on some things. Obviously, the camera can only do so many things at once. When it comes to preview, we choose to compromise on quality. We care much more about latency. We want the user to be able to see what the camera sees much faster. This just generally results in better latency because we're able to compromise, as I said, on quality. Some of those compromises come in the form of, for example, reduced motion stabilization or less noise reduction. Moving on to the photo pipeline, you may want to enable our users to capture high-quality images. Keep in mind that, as I said before, one configuration in, one frame out. Different frame configuration may mean that you will not be able to reuse the same raw frame. One example of this is if you are requesting different exposure. So at the physical level, the sensor needs to expose the frame for a different period of time. That means that you're going to have a different frame entirely. If you are mindful while you set up your pipelines, you may be able to avoid this compromise entirely. So when it comes to photos, we care much more about the quality, a lot less about the speed. So we choose to compromise on that latency in lieu of having much better quality image. Lastly, we have the video pipeline. This is for the video record use case. As the diagram indicates, you're seeing that all these pipelines should be parallel in theory. In practice, we have a number of bottlenecks, and frames can only come so fast out of the camera. Some of those bottlenecks include the exposure time. Some of them can be the processing power, memory, bandwidth limits, and a number of other things. In the video pipeline, it's almost a blend of the previous two. We care about the speed. We definitely need to have frames coming consistently out of the camera at a certain rate. But at the same time, we also care about quality. So it is very important that in this kind of use case, we find the right balance. Generally speaking, we can only test for so many things. Android runs in many, many devices, not just the high-end, but you're talking about low-end too. Unfortunately, we can only test, as I say, so many things. In general, the best tested scenario is when you have preview pipeline running plus one other. You're going to have a really hard time if you want to have all three pipelines running simultaneously. So we discussed trade-offs made by the hardware. We discussed trade-offs made by the framework. And now we're going to dive into the application layer, what we as developers can do. Let's walk through the end-to-end process of a frame. From the creation of a request until the pictures are finally in memory ready for us to use. Follow the steps, easy as ABC, and then profit will just fall on your lap. If you don't believe me, ask Snapchat. The first decision you have to make as a developer is selecting the right device out of the ones available on your list. Device here means the camera module, not devices in phone device. Each phone may have multiple cameras. Generally speaking, you probably have at least one front, one back. This is especially important now that we have multi-camera APIs. You may have multiple devices that are, say, back-facing that you can choose from. So you'll have to go through those devices and see which one fits your use case best. Once you've successfully opened the camera, you're going to get the camera device instance. And that is necessary to proceed forward in the open camera callback. You can use the very same callback to monitor the status of your camera device. It is entirely possible that the camera may be yanked from you if a higher priority process requests the device. This could happen very easily in a multi-window environment, for example. Second step, you need to allocate your camera output targets. This is where each of the pipelines that we showed earlier are going to copy your frames in the form of buffers. The memory may already be allocated. Then all you need to do is to get a reference to the underlying surface and pass it as a target. Otherwise, you may have to wait for a callback. Once the targets are ready, the capture session, which is specific to the device that you open, can be created. It is worth noting that, as I said, the camera capture session is specific to that device that you opened earlier. Once the session is ready, you can build a capture request. One of the predefined templates must be used. If you don't want to take any of the hints from the system, you can use template manual for full control. Otherwise, the framework is going to provide a set of templates that closely align to the camera conceptual model we discussed earlier. So you have templates for preview, you have templates for photo, and you have templates for record. The capture request contains specific frame configuration and the output target. Recall, frame configuration in, output frame out. A couple of things to know is the output target must be one of the previously defined ones. You cannot just use another surface here and attach it. It needs to be one of the surfaces that you declare first as part of the session. This is the configuration part of it, of the configuration in, frame out. To recap, we've chosen the camera device that we want. We created the camera session for that particular device. And now we built a capture request that will be used in that session. We can finally ask for a camera frame. We send the capture request to the session, and then we wait for the callback. We can do this in two ways. We can send a request once, and we can make it repeating a request. This makes more sense in use cases like, for example, preview or video record. You don't want to be sending a configuration for every single frame. This is a very easy way to just send one configuration and ask the framework to continuously repeat it. Now, which callback do you want to listen to? That really depends on what you want to get out of it. If you want to get the frame metadata, you should look inside of the capture callback. If you want to get the frame for CPU processing, one of the options is using image reader. Generally speaking, you can just get whatever pixel information out of the output surface that you have set up. Image reader is just one of the easiest ways to do it. If you want to get that into the GPU, a great idea is using random script allocations. Obviously, that's not the only choice. You can also use OpenGL texture buffers. And this is the cycle, step 1 through 5, that we need to go through for every single frame. Recall, one configuration in, one frame out, and a bunch of trade-offs in the process.
All right, thanks, Oscar. My name is Mustafa Abrar. I'm a software engineer at Snap, and so I work on the Snapchat app. Today, what I want to do is take what Oscar said about the lower layers of the camera and sort of work up to your app and design choices that you make and how they influence how you interact with the camera. We'll talk about some trade-offs in terms of architecture, how to architect the camera framework inside of your app, and we'll talk about specific challenges in sort of a more narrow use case. So nowadays, if you've ever used Snapchat, I'm hoping everyone has, the first thing that happens is it opens directly into the camera. And the reason for this is that people use the camera now as a means of communication. They're taking a picture, they're adding metadata, creativity, and then sending it. And so it's really like the cursor, where what do you have to say? And trying to get that out as quickly as possible is sort of the thing we really value. There are a few key camera design decisions that we've made, and these will influence how we interact with the camera. The first of those is full screen. In video, in pictures, front camera, rear camera, all of them are full screen. Now, you typically don't see this on a lot of cameras. If you take your camera out, usually picture mode is 4:3 aspect ratio, because a lot of times you share it online. The camera actually optimized for specific aspect ratios. And so since your display is usually 16:9 or some other aspect ratio that might not be available for picture mode, we have to make a trade-off. Usually, the devices will have something that matches, but it might be really high resolution. And to just encode that and create a JPEG out of it just takes a long time. So we have to make trade-offs in terms of the resolution we select for taking pictures and video and so forth. The second part is single mode. There's no video mode. You don't swipe and enter a video mode. And when you have this design choice, it leads to a set of optimizations you can't take advantage. For example, videos, there's a recording hint on Android that you can tell the system the user is about to record. There's a lot of optimizations that you can set, but if you don't know the user's intent, if they long press, it's a video. If they just take a picture, single tap, you don't know ahead, so you can't decide up front what configurations are always going to work. We try to do static configurations that are good in a lot of scenarios, and then we have certain that are dynamic, and we update those depending on what the user's intent is. The other part is, for a long time, Snapchat has offered lenses, a lot of interactive features inside of the camera. And each of those things forces certain trade-offs. For example, if there's a lot of motion, your face is moving, and you're trying to track a user's face, optical image stabilization, there's a lot of things that might not work well with these other things that want to keep track of where the user is. Also, it has a lot of memory overhead. There's a lot of GPU work going on, and you need to balance all the work that you do. The last part is you can't cheat. You have to capture the picture in front of the user so they can get their message out as fast as possible. Most cameras, if you take a picture, it hides the latency and it saves it in the background. So you don't see it. It just kind of falls away, and you don't really see how long it actually takes. But for us, because the real meat is when users edit the canvas of their image or their video, we have to do it right there and then. And so you have to make certain trade-offs to have low latency to get there. Now, to support these and some other features, you need to kind of think about how the overall architecture of your app is going to be if you truly want it to be universal. So there's a few best practices that I'll share. Some of them really just sort of help and broaden the width of devices that you're able to target, and also how well they perform on those devices. And over time, you're going to add features, lenses, interaction. So you want a framework that's extensible so that you could plug and play different things. So the first thing you have to interact with is the API that Oscar mentioned. It's the part you interact with the camera, and there's a set of APIs. There's two versions. There's Camera 1, and it's been around for many years. And then there's also Camera 2, a newer API. Although Camera 1 is deprecated, when you have hundreds of millions of users, it's a big chunk that's still on Camera 1. So you need to support it regardless of what the device says. The second part is there's different modes for Camera 2. For OEMs to slowly adapt, they have a legacy mode, which is simply, we've made our API work, but under the hood, it's really Camera 1. And also, Camera 2 varies by device. Some devices say, yep, Camera 2 works great here, but in reality, deep down, it's still Camera 1. And so the performance you get might vary even across devices. So you really need to know each of the different products that you want to target. And so what we do is we support both. Since 2016, we've written both Camera 1 and Camera 2 in terms of code. And then what we do is we add a layer on top that's basically what our application sees to just unify what it looks like underneath. And then if you have shared code, for example, picking resolution, it doesn't really matter which version you're using. The logic for the full screen that I mentioned can be shared by both. So there's some shared code, but the application deals with the top part. The next part is there's millions of devices. A lot of them have bugs. They say they support a certain feature. It doesn't work. You zoom in beyond 99%, some bug comes. So we have a lot of configuration that allows us to decide on specific devices and models what behavior, what configuration to adopt. And so this remote configuration is really key. And over time, you have to groom it. You have to maintain it. It's a very key part of something that's just code. Now, let's build up this architecture. So I've talked a bit about sort of the camera interaction, the code that talks to the camera server, which is the Android system process that manages the camera. And it talks through binder IPC, which is a form of intra-process communication. But if you expose this to your applications, it's a little too raw because you might have a video chat feature, a camera, and video note. And if they all try to talk to the camera, they could do things that sort of conflict with each other. There's life cycling, a lot of things you need to be aware of. And so what we do is we have a queue, an operation queue, that allows us to coalesce things that are redundant, allows us to manage sort of invalid states. And so we avoid a lot of conflicting things across features by having an operation queue and a thread that processes them. And the next part is, so everything on your right, the gray side, is really about the UI. Like the shutter button you see, the autofocus, the animations, all that. And then it has a state machine that says, OK, the user tapped to autofocus. Let's do the animation. Let's ask the camera to autofocus. And then it saves your intent in memory and tries to drive the asynchronous process to get it done. And so the right-hand side and the left-hand side have sort of different responsibilities. And then over time, your surface comes in. That's the preview frames that Oscar was saying. It starts showing up on your screen. If you have interactive features enabled, like lenses, they get composited on top of it. And this is done in OpenGL. And we try to do it synchronously and not avoid copying anything large. And then ultimately, your UI is composited on top. And so as far as the user is concerned, it all looks integrated. But in reality, it's multiple layers that are coming together. Now, if you look at this architecture, what you notice is that the left and the right have sort of different things that you're concerned about. And one way to think about it is client-server architecture. The right-hand side is like the client. The left-hand side is your runtime, your processing. And the concerns are different. So from a performance perspective, the left-hand side needs to worry about processing frames really fast. It needs to worry about stability, a lot of things. And the right-hand side is really about animations, new features, a lot of the candy in terms of how the user interacts with the camera. And so one cool thing you can do is, if you ever work with client-server, is sometimes the server is slow. It takes hundreds of milliseconds, sometimes some issues. So what we do is we have ways of replacing components. You can use Dagger. You have other approaches where you say, OK, let's just abstract out the camera so that the UI thinks it's talking to the real thing. And we'll just mock the APIs to the Android system and maybe do a no-op or send black frames, whatever we want to do. And one place where we take advantage of this is performance testing. So for example, if you add new UI logic and you want to see if it regresses the camera in any way, you don't care how long the camera operations take. And because they're variable, if let's say it takes 100 milliseconds to open the camera, and it's variable because it's a system service, then over time, you might not be able to catch 10 millisecond regressions. And so in this example here, what I'm showing is a startup regression test with a mock camera. So the camera's been mocked out. It's starting the app repeatedly and saying, OK, let's collect the metrics and see how long it's taking to get to a stable point. And then we can actually catch regressions across several commits to see what change might have caused it. Another example is, instead of replacing the whole camera, you can replace part of it. You could say the frames that are coming out, let's just replace them with something else rather than the whole camera. You could keep other functionality intact. And so in this case here, we could replace the frames with a video file. And so this is very useful in situations where, let's say, you're automatically testing your face tracking. In the lab environment where you run integration tests, there's no faces. There's no people in the lab to look at the camera. And so what we do is we actually use the video files to drive that interaction. So here's a picture of me running some lenses testing where the frames have been mocked out from a video file. And so there's me. Hello, I/O. And you can see the paper showing it's not the camera. It's just a video. But everything else is real. It took a snap. It edits it. It does a lot of things. So you can mock out parts of the camera to allow you to add new features and just test things in isolation. And so this is kind of, in terms of an architecture, it's one way to do it. There's many ways. But this gives you the performance considerations on the left, the remote configuration to get a wide range of devices supported that have different cameras, multiple cameras, like front-facing, rear. And so the remote configurations for that, the performance considerations, and the UI and the extensibility. Now, let's jump into a specific use case. Snapchat's known the majority of our media is just images. And everyone always asks, how do you guys take photos? How does it all work? And we break it up into several stages. The first stage is capturing, quickly capturing the content so that you can actually process it and allow the user to be creative. Once they're at all their creatives, you composite all of the different layers of creativity that they've done, and you transcode it into something that is efficient to transport over the network to the recipient. And the last part is rendering. That's the part where the recipient looks at the content, and depending on the choices you make in your player, can really affect the quality of the image that they see. And all of these are complicated things, and we have teams dedicated to each one. But I'll just touch on the capturing one for today. Now, Oscar mentioned you tell the camera, hey, capture a frame, and you wait back, and your callback is called. But there's a lot of latency involved in this step. In camera 1, the API is called take picture. And it takes 400 milliseconds on a really high-end phone from last year. Whereas if you take the preview frame that's optimized for low latency, it's an order of magnitude smaller. And you can see the P90s are quite high. And so what we do is periodically we'll optimize as much as we can our code for specific devices that we feel are pretty good latency, and we enable it remotely for users on those devices. And users are delighted. Wow, the quality went up. It looks really cool. It just happened today. People will notice it right away. But also, they notice the delay. And if you're trying to communicate and there's any lag or anything, you'll notice it right away. And so what we do is we try to do a trade-off. We do both. We'll take picture and screenshot on certain devices. And if it takes too long, we fall back to the screenshot. So we have a lot of tricks to sort of work around this. You can see examples here where the quality, when you really zoom in, is noticeable. But it's not always a slam dunk. In this case here, take picture on the left is causing noise. And sometimes the algorithms might overcompensate, and you'll see speckling. So it's not always just turn it on. Certain front-facing cameras, we disable it, even though it can sometimes result in higher quality, especially in low-light conditions. So we balance that. And so really, it's a hierarchy of trade-offs. Oscar talked about the low level. You've got the design choices of what you've decided in your application, and ultimately user intent. Is the user sending a picture to someone that's disappearing, and you want to favor latency, versus is the user preserving something? So hopefully some of the tips we've shared will help you guys build a better camera app. Thank you.
Thanks, Mustafa. Hi, everyone. My name is Vinit Modi. I'm the Android Camera Platform PM. Oscar earlier identified a series of trade-offs required to use the camera to APIs. Mustafa further elaborated on that theme on how they apply those trade-offs in the real-world situations. I'm going to change the conversation a bit and talk about how working together, we can truly elevate both the developer and the end-user experience. The camera is evolving today. It's moved on from mere photography as an immersive medium. A great example of this is what was demonstrated in the keynote by Parna, where the camera is now used to do geo-navigation. In addition, cameras are everywhere today. From IoT devices, there's a great example in the Android Things booth, to your laptops, to multiple cameras on devices. And that's a trend that I want you all to take away. Devices with more than 2 cameras are becoming the norm. Recall the camera model that Oscar talked about earlier in the talk. How do you extend that model in a multi-camera situation? Let's walk through an example. Imagine a device with 3 back cameras. The native camera app today has access to the physical streams from each of these sensors. In addition, the native camera app has something called the logical camera. This is a virtual camera. It's made up of all the physical sensors. It is a combined fused stream, and it takes care of some of the trade-offs that Oscar and Mustafa alluded to in terms of power, performance, and latency. So in the native camera app, you actually have 4 cameras, 1 virtual, 3 physical, in a 3-camera device. But as developers, you only get access to 1 of them. This often depends on the different types of devices. And in this case, you end up making trade-offs. You're using the APIs differently from the native camera app. So we're pleased to announce that starting with Android P, you'll get access to all the cameras, from the logical camera to all the physical streams. This applies to both the front and back sensors, as well as many different form factors. Here are some example use cases. The lady in the picture, this is an image of a bokeh mode. You can use this new multi-camera API for depth, optical vision, getting monochrome frames directly from the sensor, and many more. But most of all, we're excited of the use cases that you guys are going to build. So let's walk through this API real quick. The first thing you would do is check the camera characteristics and check if the device supports the logical multi-camera API. Next, you would check to see which physical cameras make up this logical device. Today, we start support for RGB and monochrome, and we're looking to add more. Here, it gets very interesting when you have a logical camera that is abstracting 1 front and 1 back sensor. Finally, you would check to see if the frames from all of these sensors are synchronized. So I know what you're thinking. Great, new API. Which devices will support it? Is it worth your time to invest in this new API? The answer is yes. Starting with Android P, all new devices will support this new API, and we're working with many partners to ensure that upgrade devices also support this API. So let me call out a few partners. We worked very closely with Huawei to ensure that monochrome sensors are supported. They actually helped us test this API. We worked with Xiaomi to ensure that a majority of their devices support this API as well. So later this year, you'll see devices from both Huawei and Xiaomi supporting this new multi-camera API on upgraded new devices. And finally, the Android One team. We worked with manufacturers from this team to ensure that this API works across all tiers of Android and is not exclusive to just the high tier. I want to share that together, we really can elevate the camera experience. Working with you, our partners, our manufacturers, we're really trying to make sure that we can bring amazing experiences. And most of all, we're very excited to see what you're going to build with these new APIs and knowing what trade-offs you need to make using these APIs. We'd love to continue the conversation in the after-session meeting space. And thank you, Oscar and Mustafa, for sharing their insights. Thank you, Snap, for giving a glimpse on how millions of users get a delightful experience. Thank you, everyone, for attending. Enjoy I/O.